Hello, this is the first part of the chapter 5.3, and we will talk about the diagonalization of the matrix and work through several examples of matrix diagonalization. Okay, so why do we want to diagonalize the matrix? The most important need for this is that any applications when our matrix, say A, is raised to the power K. And there is a multiple needs for this kind of powers. For example, Markov chains, like for the demographic applications or for the banking applications, often require raise big 1,000 entries matrix to the large powers, hundreds or so, like when we are trying to find long-term solutions. The graphics application do it. The machine learning application often do it. So the need is humongous. But the problem is matrix multiplication is really slow. If we're raising matrix A to the power by multiplying it by itself, it will take forever to run a simulation. So there is a really, really urgent need to come up with the idea which has less to do this raising matrix to the given large power pretty fast. And the diagonalization is really, really help us to speed up this power process. And the diagonalization, you already actually saw it, at least part of this process. In the previous lectures, we were looking at the similarity of the matrix, and we say that the matrix A and D is similar if we can find the matrix P and its inverse P minus 1, then we can write the matrix A as a product of P, D, and P minus 1. And you probably was wondering, why do we even bother with this similarity? Why is it needed? Oh, it's because for diagonalization, we take a very special similar matrix D. This is what we call a diagonal matrix. So this is the matrix which has some non-zero entries along the diagonal, and everything else is zero. And this matrix is really beautiful. It's really easy to raise it in any power K. For example, let's just look at this matrix D. It's, again, this diagonal matrix. Left diagonals have entries 5 and 3. The rest entries are zeros. So let's try to square this matrix. We're basically trying to multiply this matrix on itself. And because we have so many zeros, we are reducing our multiplication to just raising our diagonal elements to the second power. So let's try to do the third power of our diagonal matrix D. And again, we multiply our matrix D by the previously calculated matrix D squared. And again, when we multiply the row by the column, the diagonal elements are the only one which multiplying. So again, we're rising diagonal element to the power 3. So we can write down like equation for matrix D in any power. All we have to do to write down matrix D in the power K is take our diagonal element and rise it to the power K. So it's a really, really convenient to calculate. Okay, so now let's take another matrix, and that one is not a diagonal. So, but let's still try to raise it to the power K using diagonalization. So we are given the matrix P and its inverse, which can produce the similar diagonal matrix D by the multiplication. Okay, let's try to do it by first calculating the inverse of our matrix P. Okay, so now we have P, P inverse, and diagonal matrix D. So we can form a diagonal matrix A and raise it to any power we want. Let's just start to the square. So we basically take matrix A and multiply it by itself. And we're working with this diagonalized form of matrix A. Okay, so let's just work with this expression. Let's take the PD and factor it out to the left. We also at the end take d times p minus 1 and factor it to the right. So then what we left in the middle is just product of matrix P inverse by itself, matrix P, which is always an identity matrix. So we just can get rid of this term. And what we end up is the product of D times D sandwiched between the matrix P and inverse. Or it's D second power of matrix D, which is, again, because our matrix D is diagonal, we just raised our diagonals in the second power, multiplied by P and that P inverse. And again, I'm not going to calculate this matrix, I'll leave them as they are. Let's just go ahead and raise matrix A to the third power. And again, we take the diagonalized form of matrix A and multiply it by the A squared, which we are calculated in the previous step. And we will keep it in terms of diagonalized matrices. And again, here in the middle, we again had the product of matrix P inverse by the P, which is again gives the identity matrix. So again, we end up with matrix D now raised to the third power, sandwiched between P and P minus 1. So I think you kind of picked up the pattern at this point. So let's write down an expression for matrix A into the power K. So again, we start by writing matrix P multiplied by our diagonal matrix D in the power K and multiplied again on the inverse of matrix P. And here are all the three matrices. You can just calculate the row by column multiplications and you get this rather messy but still workable expression. Still, it's much, much faster than any other way we could calculate the power of our matrix A. So it seems to be really good algorithm, but is there always a way to diagonalize the matrix? Actually, this theorem 5, the diagonalization theorem, give us a very important conditions for diagonalization. So for matrix A, n by n matrix, to be diagonalizable, it requires that it has n linearly independent vectors. So basically, our matrix A is diagonalizable if and only there's enough eigenvectors to form the basis of Rn. And we call this basis as eigenvector basis of Rn. But when we have this eigenvector basis, the life is truly beautiful. We can take our eigenvectors, put them into the matrix, and they form our matrix P. Then we can take the eigenvalues, put them in the diagonal of the diagonal matrix, and we will get a matrix D. So there is a really, when we are, all the conditions of our diagonalization theorem exist, we can come up with a very clear algorithm for diagonalization, and we will talk about this algorithm in the next part of this series.